Alright everybody, welcome back. This is section 7.5 of AP Calculus BC, Approximating Solutions Using Euler's Method. Okay, so first off, what is Euler's method? Euler's method is a technique that we can use to approximate the value of a function at a specific point, specific x value, even when we don't know what the function is. What we do need to know, not the function, but we do need to know the differential equation and we also need to know an initial value. And as long as we know those two things, we can use Euler's method to approximate the value of the function at a given point. Okay, so how does it work? Well, if we know the derivative of the function and the value of the function at a point, what we can do is we can keep finding linearizations that give us new approximations until we finally arrive at an approximation for our desired value. I'm going to show you what this looks like. We're going to look at this graphically. You see the solution curve y equals f of x for a particular differential equation in this graph here below. But realize that in the scenario where we're using Euler's method, this is a graph that we can't see because we don't actually know what it looks like. We don't know what it is. What we do know is we do know the value of the differential equation for various x values, and we know a single point on this curve. This point right here, the initial condition. And if we want to find an approximation for the value of this function at x sub 5, Euler's method is a perfect technique for us. Alright, so let's see how it works. Here's what happens, is I'm going to use the differential equation to find the slope of this function. Again, remember, we can't see this function, but we can find the slope at this point. And using the slope at this point, we can find a linearization to the curve at this point, which I'm going to go ahead and try and draw in here. See how well this goes. Oh, not too bad. Alright, there's my linearization at x sub 0. And then what I do is I use that linearization to approximate the value of the function at x sub 1, which now is my new estimate for the function. And you can see that that's off from where it actually is. Of course, I couldn't tell that in reality because I don't know where this curve is. You're going to keep hearing me say that. Alright, and then what I'm going to do, what I can do, is I can, using the differential equation, find the slope at this point. Even though I don't even know where that point is, I can approximate the slope at that value. And I'm going to go ahead and approximate the slope of the curve at that value. And let's see if I can draw in the line that's tangent to the curve at that value. Alright, not too bad, pretty close. Now what happens here is I'm not approximating this from the curve itself. I'm approximating the value from this previous approximation. And so I would draw, the line that is parallel to that because I don't actually even know where this line is. And then that line produces my next approximation, my approximation for x sub 2. And then I do that again. I find a linearization by using the slope of the curve at the point. I use that slope with my previous approximation. That gives me a linearization. And ba-boom, there's my approximation for the value of the function at x sub 3, which you see is really close. And I could continue to use these linearizations. I could find I'm not going to take the time to draw the line. I could find the tangent line there and use that to create a linearization, which then gives me an approximation right about here for the value of the function at x sub 4. And then I could use the slope of which I can find from the differential equation, and then draw in a tangent line to that. And maybe that would give me an approximation right around here, which is actually pretty close to the true value of the function in this particular example. All right, not always going to be necessarily that close, but this is a way that we can approximate that function value using Euler's method. All right, so that's what's going on behind the scenes. We're starting at a point, we're finding the slope of that point, we're using a linearization to make an approximation of the next point. Then from that approximation, we use the slope that we know at that x-coordinate. We use another linearization to create another approximation. And we continue down this until we get to the spot where we wanted to find our approximation. All right, that's how Euler's method works. Now let's see how this actually works in practice. So a little bit more narrative here. What we see here with this estimation is what we do is we approximate the slope of the curve using the differential equation. We did that. And then every time we found a new approximation, what we were really doing was we were taking that dy dx that we found and we were multiplying it times the change in x. And that gave us the change in y. Let's go back to the previous slide for a second here. So when we took this line, what we did was we took dy dx, which is the slope of this line, and then to get the next approximation point, we multiplied that by dx, which gave us our dy that we added to the function to produce the new approximate value for y. All right, and then we take that change in y that we found, we added it to the previous y, and we got a new y. That's how Euler's method's going to work. Let's look at an example in practice, algebraically and numerically here. Example 1. Using Euler's method, approximate the value of f of x at x equals 1.5 if dy dx equals x plus y, and y of 1 equals 1 using a step size of dx equals 0.1. So I'm a big table using guy for Euler's. Some people will just use equations. I really like to use a table to help me organize my Euler's information. I always organize it into 4 columns. My x sub n column, which has all my x values starting at the initial x value, which we got from here, and going all the way down to x equals 1.5, which is where we wanted to find our approximation. I have a column for my y values. The first y value I'm going to get from this initial condition right here, that's 1. And then I have 2 more columns, one where I find the value of dy dx at this point, and one where I do this calculation, starting with my previous y, adding in dy dx times dx to get my new y. And then my new y is going to transfer over to the next row of my table. So let's show you how this works. X and y, both 1. Dy dx is equal to x plus y. So 1 plus 1 equals 2. That's my value of dy dx. So my new y is going to be my old y, which is 1, plus the value of dy dx, times the value of dx, which is the change to go from one x value to the next. In this case, that's 0.1. We were told that in the problem. And this gives us a new y value. And this I'm going to bring right over here, and that's my new y value. That's my estimate, my approximated value for the value of the function at x equals 1.1. Then I calculate dy dx using these 2 values. So it's 1 plus 1, 1.1 plus 1.2. So dy dx is 2.3. And then I take my current y plus dy dx times my dx. Let's see, that's just going to be 0.23. 1.2 plus 0.23 is 1.43. I have a feeling I'm going to need to use my calculator sooner rather than later in this problem. And then I bring that down. That's my new y value. I calculate dy dx by adding these 2 together again, because that's our dy dx. And then I go with previous y plus dy dx times 0.1. I'm just going to go ahead and punch that up. 1.43 plus 2.63 times 0.1 gives me 1.693. That's going to be my new y. So dy dx, I add these two together, that's 2.993. And so then I've got 1.693 plus 2.993 times 0.1. So I got 1.693 plus 2.993 times 0.1, which is 1.9923. I'm going to bring that down. That's my new y. I find dy dx by adding x and y, because that's the differential equation. We don't always do that. That's determined by the differential equation that we're given. And then I have old y plus dy dx times dx. I'm going to go ahead and calculate that. So that's 1.9923 plus 3.3923 times 0.1, which is 2.33153. And then I bring that down, and when I hit this bottom row, I'm done. This is the value of y, that is the approximation for the function at x equals 1.5. And so we are going to approximate that the value of f of x in this particular problem is going to be 2.33153 at x equals 1.5. All right, so that's what Euler's method is, a peek behind the curtains at how it works, and then a first example of setting up an Euler table and using that to calculate the approximation at a given point. All right. That brings us to the end of this video. We'll come back next time. In the next video, we are going to look at a couple of old free response questions that involve Euler's method, and even in one of them a preview of coming attractions for this unit. All right. Hope everybody has a great rest of your day. See you next time, and bye-bye.